So today we get to use the cross product in some applications, and the first one we're going to look at is area. Okay, so for this parallelogram, I'm going to label it A, B, C, and D. I know to get area of a parallelogram, I need base times height. So first thing I'm going to do is look at this corner here, angle B, and drop my height maybe just a little bit closer, right there. So if I look at sine B, I can say that that's the height over the magnitude of BA as a vector. That would be my hypotenuse. So the height itself would be the magnitude of vector BA sine B. Okay. The base would be the magnitude of the vector BC, if we're thinking in terms of vectors. So base times height would be magnitude of BC times magnitude of BA sine of the angle between them. That is looking strangely like the cross product. So I can write the area of this thing would be vectors BC cross product vector BA. So the parallelogram formed by vectors BC and BA, I can find the area formed between them with the cross product. That's kind of cool. So let's try one. I have a parallelogram with vertices P, Q, S, and we're missing R. So I've been asked to find R and then find the area of the parallelogram PQRS. So by convention, we tend to go P, Q, R, S, round and round. We go in alphabetical order. I spent 15 minutes, maybe one class, 1 year, trying to draw a parallelogram in 3 space, and it really was a disaster, so I'm not going to with this one. We're looking for that vertice. I have P, Q, and S given to me. So first thing I want to find is R, and so if it is a parallelogram, then my side or vector PS should be an equivalent vector to QR. So I can find vector PS. I have the S subtract the P component, so I'd end up with -3. 4 subtract 1, 3. And 5 subtract 1 is 4. So vector PS in component form would be -3, 3, 4, and QR would be R1. Maybe I should just say let R be R1, R2, R3, just to define. So I would have R1 subtract 3, R2 subtract -3, and R3 subtract 4. So solving for each one, R1 would be 0. R2 plus 3 is 3, so R2 would be 0. And R3 would be 8. 8 subtract 4 is 4. I'm good. So I have found R. It is 0, 0, 8. Find the area of the parallelogram. So I am finding the area formed by either set of vectors. I'm going to go with PQ and PS. So I'm looking for the area of the vector, area of the parallelogram formed by the 2 vectors, PQ and PS. So area would be the magnitude of PQ cross product PS. Well, the nice thing about the cross product is I can do down products and up products. So I want the magnitude. Where is P? PQ, or can I find PQ? PQ would be, so 3 subtract 1 is 2, negative 4, 3, cross vector PS is negative 2 subtract 1, negative 3, 3, and 4. There we go. Oh, sorry, I already did that one. So we're doing the cross product of those two. I'm going to just step a little lower here and do my cross product, down products, up products. So 2, negative 4, 3, 2, negative 4, 3, negative 3, 3, 4, negative 3, 3, 4. So for the cross product, get rid of the two ends. Down products would be negative 16. The up product would be 9. Down, negative 9. Up, 8. Down, 6. Up, 12. Subtract those. If you can read my writing, negative 6 subtract 9 is negative 15. Nope, I did something wrong. Yeah, can't do math. Negative 16 subtract 9, negative 25. Negative 9 subtract 8, negative 17. 6 subtract 12, negative 6. So to find the area, I want the magnitude of negative 25, negative 17, negative 6. So my magnitude is negative 25 squared plus negative 17 squared plus negative 6 squared. 625, 289, and 36. Square root of 950 units squared. Approximately 30.8. So that's cool. That's probably the fastest way you've ever found to find the area of a parallelogram. Also, it's asked us to find the area of the triangle PQS. Well, you'll never believe it, but the area of a triangle is half of the area of a parallelogram. So we just need to take half of the magnitude of PQ cross PS, which would be half of the root of 950. Or approximately 15.4. All right, then. So area of a parallelogram, and we can go from there for area of a triangle. The second thing we're going to look at was on the back of your handout from yesterday. Okay, here goes. Me and Torque are not the best of friends, but we have a bicycle pedal. And if you would forgive my drawing, this is the pedal. So it is black because it is made out of rubber. And here it is. And it is attached to my purpley reddish bike. And so this would be a nice screw where it's attached to the bike. So this is like our pivot point on the wrench. So my vector would come along the length of this. This is important, this vector. The longer that is, that can add to your force. It is 0.15 meters long. 0.15 meters long. Okay? And the force is coming down on the pedal from my foot. I'm not going to draw my feet because they are very big. So this is a force coming down on the pedal from there. And we want to determine the magnitude of the moment of force about A. We're also going to determine where this force is going in. So we have vector A. And so the cross product, like the dot product, is where we are thinking about those two forces tail to tail. So I'm going to draw it like I did with the wrench, where we have that force of 75 newtons tail to tail. So I need the angle between them, as crooked as that drawing is. So I have created basically a Z pattern. So there is 80 degrees between the length of that axis and the force, which is the 75 newtons. So my cross product would be the moment of force or the torque. We call that M. And that would be a cross product. I need the magnitude of, I need that distance, 0.15 times the magnitude of the force in newtons. I'm going to do it in the right order. Should be newtons first. 75 times the 0.15 sine 80 degrees. So we're getting Newton meters, 11.1. Some of you are saying, oh, lady, a Newton meter is a joule. Not exactly. It's not a linear force. It's not going in the same direction. It would not be a joule in this particular case. Okay, so I want to summarize this somewhere. I just want to use the right letters of the alphabet. So it's a 3D force. When you're pushing on the pedal of a bike, your force is going into the bike. You're pushing down on the pedal. It pushes the force into the wheels of the bike. It then pushes it forward, which confuses the life out of me. But my moment of force is going to be the magnitude of the length. Let's write this as the cross product of the force and the displacement of that distance of the axis. Okay, so that is the magnitude of the moment of force. We've also talked about the direction. In this particular case, if I used a right-hand rule, my pointer finger would go along the 0.15, and the 75 newtons would be my middle finger. And so this force would be coming out of the board at us. So the bike must be standing approximately where I'm standing, and that pedal is just beyond us, pushing the force into the bike. Okay. Our next thing is using the dot product. So Jordan is pulling Ben in a toboggan and exerting a force of 40 newtons acting at 24 degrees to the ground. If Jordan pulls him 100 meters, how much work will be done? So we've got Ben in a toboggan. So I'm not going to try a toboggan. Just got Ben. Okay. And he is being pulled 40 newtons, but not just directly forward. There's kind of an upward pull as well. And looks like he's pulling him on grass. But anyways, 24 degrees to the ground. And we want to know the work being done. So work is the dot product of the force over the displacement. Work is the magnitude of that force, the magnitude of the displacement, cos the angle between them, which is 40, that was the force, 40 times 100, it needs to be in meters. Where did it go? 100 meters, there we go, times cos of the angle between them. We get 3,654, and we've got units of newtons and meters, but this time it is a linear, everything is going in the same direction, so we can say it is joules. For some of us, we would see that work being done is the horizontal component. How much of that force is going horizontally multiplied by 100 meters. So you're going to get to the same place, just maybe a slightly different way of thinking about it. The horizontal component would be 40 cos 24. And multiply that by 100 meters that we're pulling, you would end up with the same thought. So dot product would be a linear force, like pulling something slightly off of the horizontal, and it would be the dot product. Something where your force is in a three-dimensional space, so you've got like torque, where your force is in one direction, like down the pedal, and your resultant goes into the bike, or your force is going along a wrench handle, and the force is going into the wall or out of the wall. That's a 3D type problem. You have got the cross product.